Hello all, the topic of our presentation is dynamic right sizing for power proportional data centers. We have divided this presentation into 7 sections, which are background, challenges, objective, algorithms, experimental setup, results, and conclusion. Let's take a look at each of them. Before diving deep into the paper and explaining the terms used in this topic, let's first talk a bit about power consumption in the data centers. Data centers usually use a lot of energy to maintain their servers. They consume about 1000 kilowatt hour per square meter of energy. This is about 10 times the power consumption of a typical American household. The most common data center equipment is the uh, server rack, which use a large amount of energy to maintain and cool down their components. Much of this energy is used to maintain the excessive service capacity of the data center during periods of low load. There is, of course, a monetary cost associated with heavy energy consumption, which is expected to increase as energy prices increase in the future. But apart from the monetary cost, this amount of power usage is also not suitable for environment and can cause a lot of damage. Thus, there is a dire need to work towards building energy efficient data centers. From the figure, you can see that only a few of the servers are processing requests, but we need to maintain the entire capacity, thus causing power wastage. In the perfect scenario, as shown by this diagram, we want to maintain only those servers which are currently processing requests, and all the other servers must be turned off. One approach which the paper talks about is to implement this solution, which is called dynamic right sizing the data center. This is done by allowing the servers which don't have any jobs assigned to them to go into power saving mode. Before proceeding, let's first discuss some key terms that are used throughout this paper. First is dynamic right sizing. As introduced earlier, dynamic right sizing can be defined as the process of adjusting the capacity of the data centers in real time to match the current workload. This is important because it can prevent over provisioning or under provisioning of servers in the data centers, which can lead to wasted energy and increased costs. In this paper, we talk about some algorithms which try to implement this idea and then analyze their results. Secondly, the term power proportional means to use power only in proportion to the load. In a power proportional data center, the energy consumption is proportional to the workload being processed, which means the power consumption varies based on the level of utilization of the servers in the data center. We encounter 3 major challenges while trying to come up with a solution for this problem. Firstly, servers must be able to seamlessly transition into and out of power saving mode without losing their states. In recent years, there has been a lot of research into enabling this with the help of virtual machine states, network state, and storage state. Secondly, there is a huge emphasis on these techniques being reliable, since there is an aspect of wear and tear consequences associated with a lot of toggling of these servers. And finally, the challenge that this paper tries to tackle is to determine the number of servers that need to be toggled into and out of the power saving modes during periods of low and high loads respectively. Talking about the goal of this paper, we observe that the paper talks about 3 things in detail. First is analyzing the optimal offline solution and studying the lazy structure in the solution. The second goal of this paper is to present the new and practical online algorithm inspired by the optimal offline algorithm. We will analyze this algorithm and observe that we only need a prediction of future workloads for a window size W to obtain the solution of this algorithm. And finally, this paper talks about validating the suggested algorithm. To do this, the paper uses 2 load traces from Microsoft Research Lab and Hotmail to evaluate the cost savings achieved from dynamic right sizing. Before moving ahead, let's discuss some more terms that will be used in this talk. The first one is PMR, which means peak to mean ratio. As mentioned, this is the ratio of the highest value of power used in the data center to its average value. It is an important metric in the current context because higher PMR means potentially higher savings by turning off the servers during periods of low load. And finally, we have competitive ratio, which is an important evaluation metric used in this paper. This is defined as the ratio of the cost of suggested algorithm to the optimal algorithm cost. We should try to find an algorithm that has a lower competitive ratio. Let's now talk about the cost of running the data center. We see that the total cost of running the data center can be divided into two parts, which are operating costs and switching costs. Operating cost has two components, the energy cost of maintaining active servers with some load, and the second is the cost incurred from delays caused by a smaller number of servers. Switching cost, on the other hand, is the cost incurred by toggling the server into and out of the power saving modes. This includes the delay cost, migration cost, and wear and tear costs. As already discussed, the cost has two components, operating and switching costs. This equation is same as the equation we saw in the previous slide, and it's important to understand it as it keeps coming up in almost all the algorithms this paper discusses. The first term is the operating cost, where G is the function that gives the operating cost at time t for xt number of active servers. And the second term is the switching cost. Beta is the cost of transitioning a server from a sleep state to active state and back again. The subtraction gives the increase in the number of active servers at time t compared to time t minus 1. So the switching cost is just a product of cost per server times the number of new active servers at time t. Note that if the difference is negative, which means the number of active servers decrease or stay constant, we just ignore the switching cost term. In other words, we deem this cost to be incurred only when the server wakes up. This problem is formulated as an optimization problem, where the total cost must be minimized, subject to the constraint that the number of active servers represented by xt is greater than or equal to 0. There are only two things that we need to pay attention to in this equation. The first thing is limit to the summation term, which goes from 1 to t in this case, and the second is this subtraction. These are the main components that will change in different algorithms. Let's now talk about some assumptions made in this paper. For the online algorithm presented in this paper, we will consider a window of length w. We will assume that we know the value of function g or the operating cost from the period t to t plus w accurately. Now let's discuss the already existing online algorithm for dynamic right sizing, which is receding horizon control or RHC. Receding horizon control is also known as model predictive control or MPC. Before discussing this model details mathematically, let's take a look at a real-world analogy of this algorithm. Consider a self-driving car, and here our objective is to keep this car in the middle of the road. For simplicity, we'll assume that the car is traveling at a constant speed and only the steering wheel angle is being adjusted to control the lateral position of the car. Let's use the plot on the top right to show the lateral position of the car. The vertical axis reflects the current time. Anything behind the vertical axis reflects the past, and the values to the right of it show the future. The middle of the lane is the reference. Let's use a green line to show it on the plot. At the current time, the MPC simulates the car's path for the next p time steps if the steering wheel would be turned, as seen here. P is the measure of how far ahead the MPC looks into the future and is referred to as the prediction horizon. It is often represented by the length of time into the future or the number of future time steps. The MPC needs to find the best predicted path that is the closest to the reference. So it simulates multiple future scenarios. However, it doesn't do these simulations in a random order. Instead, it does it in a systematic way. MPC also makes sure that the steering wheel angle and the car's position stay within the prescribed limits. These are referred to as constraint to the problem. At the current time step, the MPC is solving the optimization problem over the prediction horizon while satisfying the constraints. The prediction path with the smallest cost gives the optimal solution. The prediction path with the smallest cost gives the optimal solution and therefore determines the optimal steering wheel angle sequence that will get the car as close as possible to the reference. At the current time step, MPC applies only the first step of this optimal sequence to the car and disregards the rest. Based on the applied steering wheel, the car travels some distance. At the next time step, the controller gets a new measurement of car's lateral position. It might be slightly different from what the MPC had predicted before. This could be due to some unmeasured disturbance acting on the car. Now the prediction horizon shifts forward by one time step and the MPC repeats the same cycle of calculations. Because of this forward moving nature of the prediction window, MPC is also referred to as receding horizon control. So as discussed, RHC is an existing online solution for the dynamic right sizing problem. It is different from the general model as here we try to optimize over the window W instead of T. The solution for this algorithm is the solution of the optimization problem mentioned in the general model, the only difference being the addition of the prediction window. Finally, I want to highlight that we use a competitive ratio as the evaluation metric here.
Hello, my name is Anagha Bhatt and I'm going to continue with the presentation. So now we can discuss the optimal offline algorithm. As mentioned before, this algorithm makes use of the same general model that was covered in the previous slides. We assume that we know the operating costs for the entire time, that is 1 to t. So we focus instead on the switching cost. This algorithm works by finding an upper bound and a lower bound for the optimal number of servers. It finds the lower bound using the same optimization problem that we discussed earlier by optimizing for xt minus 1. But for the upper bound, we only consider cases where the number of servers decreases from time t minus 1 to time t and consider x t minus 1 minus xt. So in this way, we get an upper bound. And then we find the optimal value for the number of active servers by solving the general optimization problem, but ensuring it remains between the upper bound and the lower bound. Therefore, if it's within the given time limit, the solution is between the two limits. If it exceeds the given time limit, then it equals 0. So we solve this recurrence relation in order to find the optimal solution. So coming to lazy capacity provisioning, this is the algorithm introduced by the authors in the paper. Since the optimal offline algorithm can only predict the optimal value for a known time period, we need a better algorithm. So lazy capacity provisioning, or LCP, is the algorithm that is introduced in the paper. LCP can predict optimal values for the number of active servers for a given time period. It's called lazy because it mimics the lazy structure of the optimal offline algorithm by lazily staying between the two bounds, but while moving forward in time. So it's kind of like a mix of RHC and the optimal offline algorithm because it uses upper bounds and lower bounds like the optimal offline algorithm, but it predicts over a given time window, similar to the algorithm we saw previously, RHC. So we similarly find upper and lower bounds in this case, except we find it for the time window included. So in fact, the upper and lower bounds in the previous algorithm are actually special cases of upper bounds for LCP when the window W is 0. So XUT is actually XUWT when W is set to 0. So within the time window, we calculate it as the optimal value between the new lower and upper bounds. And then, therefore, this is a lemma which follows from the way we compute the upper and lower bounds. we can see that the new lower and upper bounds form an even smaller margin for the optimal solution to fall in. It can be found that this relation holds true with the cost. Therefore, we can say that LCP is 3 competitive when compared with the optimal cost. But in practice, the gap is even smaller because switching costs will be much smaller. This is because we would need to toggle servers only once a day because of diurnal traffic. And in addition to this, the competitive ratio is independent of the switching cost beta and the window size W. Okay, coming to the experimental setup. So for the benchmark for cost, the paper uses a static right sizing scheme to calculate a conservative estimate of cost savings. So a constant number of servers is chosen, assuming a full knowledge of the workload. And then coming to the workload information, 2 traces are used to analyze the effectiveness of the LCP algorithm. One of these is from Hotmail, and the other one is from the Microsoft Research Lab, or the MSR in Cambridge. The Hotmail trace also includes a number of maintenance tasks that are performed at night. And since we use data from 2 different traces, according to the paper, the data is normalized so that the peak load is set to 100. So now we come to the results. This paper analyzes a few parameters, and I'll only be discussing a few of them because of time constraints. So in these 2 sets of graphs, the graphs on the left are for the Hotmail trace, and the graphs on the right are for the MSR trace. So in this slide, we discuss switching costs and energy costs. So first let's take a look at switching costs. On the left, we have data for the Hotmail trace, and we can see that significant cost savings are possible as long as the switching costs are not too extreme, that is to the extent of an hour or a day or even longer. And in case of energy costs, it can be observed that the cost savings increase with an increase in energy costs, which is very intuitive. So both traces show that significant gains are possible as energy costs increase from the order of 10 to the power 0 to 10 to the power 2. And then the PMR ratio, as discussed earlier, refers to the peak to mean ratio. Dynamic right sizing exploits the gaps between peaks and valleys in the workload and provides larger savings as this gap increases. So as the peak to mean ratio increases, there is also an increase in cost savings. So it was found that cost savings go from 0 at a peak to mean ratio of 1 to 5 to 10% at a peak to mean ratio of 2. Okay, coming to additional insights. So other applications that we were able to come up with were these 3. Energy conservation is a key issue in wireless sensor networks, and this algorithm can be adapted to suit the wireless sensor networks. It could also be used in facilities like cellular signal base stations in order to conserve energy. And in general, it can be used along with any application where there are multiple nodes, and these nodes are operating under different varied workload, and there is a need to conserve energy and reduce the corresponding energy costs. So these are other potential applications for this algorithm, where we can keep the logic the same, but modify a few things based on the system and based on what we need to adapt it to, what environment we need to adapt it to, and what technologies we need to adapt it to. So yeah, those are the additional insights we were able to come up with. Okay, to conclude, there is a dire need to reduce the energy consumption of data centers in periods of low load. And this paper introduces an algorithm called lazy capacity provisioning, which is a three competitive algorithm. It also compares it with two other algorithms, and these two algorithms are RHC and the optimal offline algorithm. And it also analyzes cost savings when multiple parameters are altered, such as energy costs, switching costs, and the peak to mean ratio. And it finds that there is a significant increase in the percentage of cost savings when this algorithm is used, especially in comparison with RHC. And it is also observed that its performance comes close to the optimal offline approach. And as discussed earlier, it's a three competitive algorithm when compared to the optimal algorithm. Yeah, that concludes my presentation. Thank you.